Hello. With digital transformation and Internet of Things, we are seeing an explosion in data, and not just data, but connected data. Whether it is trying to match applicants for a job opening that you may have posted, or trying to find close contacts of a person who was infected during a pandemic, or trying to find the most economical and efficient way of delivering power to a group of consumers. Connected data is everywhere. Azure SQL DB and SQL Server provide a trusted and mature platform that you have probably been leveraging to store data of all kinds and at all scales. Wouldn't it be great if you can use the platform that you love and trust to work with this new volume of connected data? Hey everyone, I'm Arvind Shyamsundar and I'm a Principal Product Manager at Microsoft. I'm part of the Azure SQL database team, and one of my focus areas is SQL Graph. It is my pleasure to bring to you today some of the capabilities that SQL Graph has and how those can be used to efficiently and effectively represent those digital scenarios that we talked about and make those a reality. Thank you for joining. Our session today begins by trying to answer the question, why are graphs so useful? We will then look at what SQL Graph is, and then dive right into the details by looking at how you can use SQL Graph to create graph tables and then query the graph efficiently. We will then look at some of the good practices that you need to use or keep in mind when working with SQL Graph, and then tie it all together with a quick recap of some real-world examples where SQL Graph has been used successfully. We will start by trying to answer the question, why are graphs so useful? To do this, we will use the analogy of a real-world social network, whether it is a professional one or a purely social one. To start with, let's think of the entities, the things that are in this network. You have people, of course. You have universities and companies, both of which are a type of organization. You have places, which may be a city, a country, or a continent that they live in. So this is just when you view the entities, the objects, the things that are in this network. It becomes more realistic once you start tracking the relationships, the types of connections between these different entities. So as an example, a person may work at a company, they may have studied at a university, they may be located in a particular place, which may be a city, a country, or a continent. So as you can see, without these relationships, just tracking the set of nodes or the set of entities is not that useful. The key thing is the relationships between these entities. You have other types of entities in this graph, and again relationships between them. So for example, these people may be posting messages on forums. So you may have a forum which contains a message, and that message could be a type of a post or a comment, which is like a reply to that particular message. Comments could be replies to other comments as well. So you may have recursive or self-referencing relationships. This is again another example why graphs are so useful, because you can start modeling these kinds of complicated and sometimes recursive sets of relationships. You may have other types of entities and other types of relationships like hashtags associated with messages or with forums and so on. When you put all of this together in the big picture, you start seeing a fairly complicated data model emerge. And again, when you put all of this together, you may be initially overwhelmed in terms of how do I model this the most efficient way? Do I use traditional SQL tables to model all of this? Or do I have to use some other types of techniques? And that's part of the thing that we will explore going forward. But just giving you a picture of why graphs are so useful, because when you visualize this whole complicated social network as a graph, which is what is shown here, the simplicity of the relationships between these different entities start to kind of emerge. And that is going to be crucial, as you will see, when it comes to efficiently representing and querying the graph later for answering some business questions or actual questions that you may be having on top of the graph. With that initial glimpse at what a graph model might look like, let's think about what are the types of questions that you may end up asking it. To do this, we are going to use an industry standard data model which is called the LDBC social network benchmark. This is not a benchmark in our case, but we are just using it to model a social network and try to ask questions on it. The first question is a very simple one. We start with a person, we then find out the friends of that person, and then we find out the messages that have been posted by those friends. So a fairly simple looking query. We will see later how we can answer this query by using SQL Graph. The second example of a query that I want to show you is again derived from the LDBC SNB. This one is a little bit more complicated. We will use a starting point, which is a given person. We will then find out their links, whether they are 1 hop, 2 hops, or 3 hops away, and thereby identify these other persons that they are connected to. For each of those persons, we will then enumerate their friends' set of characteristics. Where are they located? Where do they work? Where do they study? And so on and so forth. So a fairly simple looking query, but the challenge here is going to be how do we recursively find paths to not just direct friends, but friends of friends, and then third level friends as well. So a fairly interesting scenario. We will see how to implement this again as we progress through this presentation. The last question that I have for a sample is again derived from the LDBC SNP, and this one is a little bit more complex. Here we are not only going to find out friends and friends of friends, so you are traversing the network, not just 1 hop, but you're doing 2 hops. For each of those friends, you're going to try to find out messages that they've posted in a particular time frame. And then we have some complex criteria derived in this particular query. We're going to say that, hey, those friends that you have identified, they should have posted messages in a given set of countries that we have provided to the query. And those countries should not be the place that those friends are normally resident. So basically, you're trying to find out countries that these friends have traveled to and posted messages. So a fairly complicated looking scenario, but again, as you will see with SQL Graph, it becomes quite expressive and simple to be able to write such complicated looking queries. When dealing with graphs, we also have to consider that a graph is also sometimes subject to the same kinds of data consistency and integrity requirements that you have with any other kinds of relational data. So for example, you may have a social network and it starts with a bunch of people, the cities that they're located in, the posts that they've made. Over time, these characteristics change. The relationships between those things may change. So for example, a person may no longer have, they may have posted a particular forum post which they subsequently delete. A person may be connected to other people. A person may lose connections to other people and so on. So as the network, as the graph is constantly changing, we have to keep in mind that there may be data integrity and consistency requirements which will necessitate the use of a highly consistent relational type system, but with the semantics, with the syntax and semantics of a graph data model. The next question that we tried to depict in our initial list of questions is, what exactly is SQL Graph? What makes it special? Let's try to answer that question by first talking about what graph databases are. So on the right here is the data model that we talked about a little bit earlier, wherein you have a social network, you have people, you have places, you have forums, and so on. When you represent that formally using the members, the properties associated with each of these nodes and edges, it starts becoming more like a database where you have connected nodes, you have edges between those nodes, and so on. So a graph database can be considered as a database which has a collection of nodes and edges. In the context of SQL Graph, these node and edge tables are actually just relational tables under the hood, but they have the syntax and the semantics that allow you to expressively say, hey, this is a related set of nodes, and then be able to efficiently query those with extensions to the T-SQL language as well. As I mentioned briefly, each of these nodes or edges can have attributes associated with them. So for example, a person may have attributes like their name, their place of residence, and so on and so forth. An edge can have attributes as well, or it can be simply empty. An edge attribute, for example, would be like the date when edge was created. An edge can be used to connect any node to any other node, and this is where things start getting interesting and where they start looking different from traditional keys in a database. With edge tables, you can connect any node type. So you can connect, let's say, a forum post or a person to a forum post or a person to a forum message or a person to a location, and so on and so forth. All kinds of relationships are possible. So an edge connects any two nodes, and those two nodes can also be from the same type. So for example, you can have a edge which is connecting a person to a person, a recursive edge as we called it. So all kinds of these edges are possible, and that is one of the salient features with SQL Graph. Later, as you will see, it is very easy to query the graph using syntax that you have probably very familiar with, which is tsql, but with a set of extensions. We will see what those extensions are, being able to easily query the graph with tsql. Lastly but not the least, these are just tables in the end of the day, so you can do all kinds of traditional things with it. For example, you can insert data into the table, you can update it, you can delete it. More importantly, you can do all kinds of query patterns as well on top of the database. Not only can you do graph type queries, which we will see, you can do traditional BI reporting type queries as well on top of the data which is stored along with those graph nodes and edges. Now let's get into the nuts and bolts of how exactly can we use SQL Graph. To start with, let's look at what graph tables are. The first type of a graph table is a node table. In the social network analogy that I gave you earlier, a person is a node, but they're also a node table in this case, because the way we represent nodes in SQL Graph is to create a node table. So node tables in SQL Graph are just like regular tables. You create them by using create table, and you specify a as node attribute when you actually create the table. The main difference between regular or traditional tables and node tables is the addition of an internal column called $node ID. Think of this as a unique identifier that SQL Graph used to represent that node in the table. Not only is the node ID unique in that particular table, but when you use it in the context of an edge, the node also takes along with it the object that it came from. So for example, in this case, a node is in the context of a person. It has a node identifier, and it also has an object identifier, which is the name or the object ID of that table. So node tables, just like regular tables, with this additional syntax added. This column, as I mentioned, is internally used to track. If you look at the object in Object Explorer in Management Studio, for example, you will see the node ID column is actually internally represented with this kind of unique identifier, but you just deal with it as $node_ID. This graph ID column is actually not usable by end users. It is an internal representation which is actually exposed through $node_ID. You just see it in Management Studio and other tools because it's a hidden column. It is important to note that in SQL Graph, the entire set of node and edge tables in a given database is treated as one logical graph. So this is very useful, and at the same time is an important detail that you should keep in mind, that the scope of a graph in SQL is to a given database. This means that you cannot really work with a graph that spans across two databases at least in a meaningful way. You could do things which are outside of the graph semantics, but in general, think of the boundary for the graph as being the database itself. So how do you work with these node tables? You start by creating the table as we saw earlier, and then you can just insert values into the node table as though it were any other table. So here is an example. You just insert values into a person table, and then when you select that data back, here's what it looks like. You will see the $node ID column, which is represented in a JSON kind of a way. Internally, it is not stored as JSON, it's just stored as an int or a big int, precisely speaking. But in order to make it useful for a user or a developer to work with, what you end up seeing is this JSON syntax. So you will see the name of the table that it came from, the type of the table that it is. In this case, it's a node table. And this ID column is actually the integer internal graph ID that's used to represent the node. All the other attributes of the property graph are available as regular columns within the select query in this case. You could note that you could also have XML or JSON values as one of these properties or multiple properties. So all the data types that are available to you within SQL are available to you within SQL Graph tables as well. Next, let's briefly look at edge tables. Edge tables is where things get really interesting in my opinion. An edge table again is just another table in SQL, but an edge table, unlike a traditional table, does not necessarily need any columns in it. You can always add columns, but it is not mandated. This is quite unique because you can do a create table as edge and that will work. How useful is it depends on your business scenario, but you can have an edge table with 0 columns in it. Most of the time though, you will typically have some properties added onto the edge table. So in this case, you will see a nose edge. A nose edge in this case connects a person to another person. So in the syntax of things, you will see a create table statement which says create table nose. And there are some interesting things that are happening here. For example, in order to specify, and this is not a mandatory thing, but it's kind of like a recommended thing in many cases, to specify that this edge is only going to connect persons to other persons, you can create a so-called edge constraint. The edge constraint, which is highlighted in green here, is specifying, as you can see, that this edge table is only going to be used to connect persons to other persons. Also, you might notice here that we can create all kinds of indexes on the edge table. I will talk a little bit more in depth about the indexing for graph tables a little later. In this particular case, to close out, you can see that the edge table has just one property or just one attribute, or in the SQL world of things, just one column, which is called k_creation date, and that happens to be a date time column. When you look at this table in Management Studio, you will notice a couple of internal columns. Just like you saw with the node table, you have an edge ID which is internally mapped to this thing called a graph ID. An edge table also tracks the from and the to. Which two nodes is it connecting in the form of the $from ID and $to ID columns. To the user or to the developer, they just see the dollar columns exposed. These internal columns are just stored underneath the hood for SQL Graph. You always work with the $to ID, the $from ID, and the $edge ID in the case of edge tables. As you can also see, you have multiple indexes, which, as I said, we will explore a little bit more in depth later on. How do you insert data into an edge table? This is again where it gets interesting. An edge table, as we mentioned, connects two nodes in the graph. And as we also mentioned, you might remember that an edge can connect any node to any other node in the graph. And that's where you have to be very, very precise in terms of where is the from and where is the to node that you're connecting. So a typical way to do this is to select the node ID of the underlying from node and the node ID of the to node that you are going to connect. So in this case, the nose edge is just connecting persons to persons. So both the node IDs come from the person table. In this case, we are trying to connect node ID for the person ID called 94 to the node ID for person ID 60,927. So the way you represent the from ID and to ID in graph tables is to use the underlying node ID values from their corresponding node tables. When you select back data from the edge table, you will see pretty much the only attribute that you inserted, which is the date at which the data was created. In this case, we inserted this value we got back that same value, but the from and the to IDs, as you can see, are clearly represented in the same kind of JSON format that we saw earlier. So it says here this from ID is coming from the person table. It has a value of 94, and the to ID is again with a person table, but this time with a value of 6927. So this is kind of saying how we kind of worked with these two from and to ID identifiers. There are some efficiencies you can do. For example, if the node ID values for your data are actually integers, that means the natural keys themselves are integers, you can repurpose that to be the node ID in the graph set of things by using the node ID from parts function. This is a very useful function which allows you to take an integer and translate that to the node ID, and you have similar functions for edge ID and so on in other cases. Very useful function. Do consider using that if you have input data which is already having natural keys of the form integers. Otherwise, as you will see later, you're inserting into the edge table, it can sometimes get more expensive because you have to join the natural keys to their graph equivalents in order to insert into the edge table. So how can we now query the graph? Now that we have node and edge tables in the graph with our data in those tables, let's take a look at some of the T-SQL extensions that allow you to quickly and efficiently query the graph. The first enhancement that SQL supplies when it comes to SQL Graph is a pattern matching extension called match. Match technically is a clause which you can add as part of your where clause, and it allows you to very expressively write statements that almost resemble this thing called ASCII art. So in the below expression, which is a simple way of looking at match in action, we are trying to find people or persons who know other persons. So it's a fairly straightforward question that we're asking, saying who all do I know? You may argue that this is just like a join, and indeed it is. In this particular case, it is nothing but a different representation of an inner join. But as you can see, this syntax is arguably easier to read, and for this simple example, of course, it might be as easy to write a join, but one of the key value props with match is you can write more complicated expressions, and those expressions can have arrows going in either direction. So as you can see, in this case, we're going from left to right. That's the way you denote the traversal through the graph, but you can have arrows going the other way around. You can combine these predicates inside a match clause and so on. So it's a very flexible way, it's a very expressive way of writing those more complicated questions that you have. Match can be combined with traditional T-SQL filters as part of the where clause as well. And if you have a CTE, for example, you could write this match as part of one expression in a CTE, and then you can have an outer query which is actually querying the CTE with further things like joins, unions, other filters, and so on and so forth, aggregates, and the rest. So match is essentially the core addition to the T-SQL syntax, match, and this addition of this expressive ASCII art type syntax. The other thing that we added is shortest path, which is a very expressive and simple way to write recursive queries. Here is an example of using shortest path to write a query which is recursively walking a tree of messages which are comments or replies to posts. So as you remember in the data model that we saw, we can have a message which is actually a reply to a post. It could be a post itself, it could be a reply to a post, or it could be a reply to another reply, which is a comment in itself. So if you wanted to walk that whole tree, here's the easy way to write, saying, hey, I have a message, how do I walk this hierarchy of messages to go to the original post? So the way you write shortest path queries is you say, I have a match, and then you say, you have a shortest path, this is an anchor. So you're saying I start with this anchor, which is this m child, which is the actual message that we are starting from, and then you start a parenthesis. As you can see here, we have a recursive part of the expression. It says walk replies of these messages all the way to a parent, and this is wrapped up with a set of parentheses and a plus. The plus there means we do not have any restrictions on the amount of hops or traversal kind of legs that it has to go through to get to its destination. And in this case, the destination is going to terminate when there is no further ancestor or no parent for that message, which is the root post. So again, it may take a little while to get used to this syntax, but if you break it down, it's as simple as you have a match. Within that, you have an expression called the shortest path, and the shortest path starts with the anchor, which is the fixed part of the query, and then you have this parenthesis, which is saying reply of parent, and that's within parenthesis with a plus, which means it's repeated infinite amount of times theoretically. Practically, it will not be an infinite amount of times, obviously. And then because you're finding paths in this case, the way you report out of that query, the way that query returns result, is you're allowed to do aggregates. In this particular case, we are doing a string aggregation over the path that we walked, and we are reporting out the messages that we visited all the way along to the root message. We count those messages as well and return those as well. So this is just an example of how you can use shortest path. The key message being you return paths, and hence you have to do these aggregates in order to return a traditional T-SQL result item, which is a scalar value, which is a specific column, and you can have multiple such rows as well. So let's take a look at some demos which will show you how to use these syntax extensions. Create table, we saw that's simple enough, but let's take a look at how we can apply match and shortest path to answer the 3 business questions that we started off this presentation with. Our first demo, we will take a look at how to implement the answer to question number 1, which was posed earlier in this presentation. As a quick recap, question number 1 involves identifying all the messages posted by friends of a given person in a given amount of time. We will see how to do this using SQL Graph and T-SQL in a minute. Here's the graph database that we've been working with. It's called LDBC SNB SF10. It has many graph tables. The ones of interest to us are the person, which is a node table, as you can see by this little dot on the table, and the nose relationship table, which is actually an edge. As you can see, it has a connected set of nodes in the icon. In addition to these, we will also take a look at these 2 node tables, one being the post and the other one being a comment. We will see how to use the match clause and be able to query the graph to find out which comments and which posts have been made by the friends of a person. There are 2 ways to do this. One is a very naive way, which is to union the set of posts and the set of comments, each of which is computed independently and finally unioned into the final result set. As you can see in this query, we start with the given person ID. So this is the person identifier for the start person of interest. The time frame that we are going to compute or that we're going to search for these messages within. Then the query is as simple as you write a match statement saying, hey, this person knows other persons, and then those persons have created messages. You do this separately for the comment and for the post tables. You run this, you will see the results being returned fairly quickly. This is a naive way because we are individually treating the comment and post tables separately, even though they are functionally similar and a message of sorts. The other approach to implementing the same query is to utilize a view over the post and comment node tables. In this case, we have declared a view which is called message, which is essentially a union all between the post and comment tables. Where not relevant, we use null values for the columns that are not present in this case in the comment table. You can use this view as part of a larger match expression, or in this case it's a simple way. We just have a match to find the friends of the initial person, and then we look at which messages were created by those friends. It's a fairly simple query, and as you can see, views over the graph tables can greatly simplify the length and the complexity of the implementation. You can also use these views as part of the match expression itself. In this case, we haven't done that, but just be aware that you can. The approach, as you can see, executes fairly quickly and is functionally identical to the naive approach that we started with initially. The lines of code for the second approach are clearly shorter than the lines of code with the initial one. Next, let's look at how we can implement a query which will help us answer question number 2. For a recap, question number 2 was to start with a given person in the graph, find the people that that person is connected to from 1 step to 3 steps away. So it's not just immediate friends, but friends of friends, and then friends of friends of friends. And then for each of the people that you identify through this query, you want to retrieve their attributes, like where they're located, where they worked at, and so on and so forth. Let's take a look at the T-SQL implementation of this query. We can implement the query to answer question 2 with 2 approaches. The first is a simple naive approach where we essentially traverse the graph to find links of length 1, then links of length 2, and then links of length 3 individually, and then union all of them together. Let's take a look at that query. As you can see, in this case, this is basically a series of matches. So the first one is paths of length 1, the second one is paths of length 2, and for each of these we are essentially retrieving the path explicitly by saying, hey, let me find immediate friends, then friends of friends, and then friends of friends of friends. So this is a naive approach, as you can imagine, but it's also fairly simple to write if you just avoid copy-paste errors. And for each of these, we are specifying the start person and then unioning all of them together. The union, you may think, will avoid duplicates, and it does. However, what may happen is that you may have paths of different lengths which all end up at the same person, and this query does not distinguish between those and retrieves all paths. So as an example, let's say when we run this, you will see that the person who you're connected to, the initial user being 94, they're connected to this user with a given first name, and that user comes up twice, as you can notice. One, they are connected with a path of 2, length of 2, and the other one, they're connected with a path of length 3. This is one of the flaws with the naive approach, because it does not really distinguish between the paths of different lengths, and will can sometimes therefore retrieve duplicates, if you may, for that kind of a scenario. So how do you solve for that? If you want to solve for that, you will need to add additional ranking functionality. So in this case, as you can see, we've ranked those paths by the length in ascending order, so that we can kind of retrieve the shortest path for a given friend that the query is returning. If you run this query, it will return a true set of shortest paths, and as you can see, there's no more duplicates for that given person that we saw earlier had a duplicate entry returned for. However, just looking at the length of these queries, they are quite huge, and as you can see, there's a large volume of duplicated code in the way that we are saying, hey, paths of length 1, 2, and 3. With SQL and SQL Graph, the more efficient way to express this is to use a shortest path expression. So match in this case can be used along with shortest path, and the way you do that is you specify the starting point of your search, which is this person table, and then you go into a recursive part of the search, which is you say that you want to recursively search for people that are known, or persons that are known by this starting person, in lengths of paths which can go from 1 to 3. So this syntax may initially look a little complicated, but once you kind of get used to it, just keep in mind that this is a recursive part of the query. This is the recursive part of the query, this is the static part of the query, if you may, and then all of that is wrapped up in a outer match. You specify the start point of the search by using a regular predicate, and then the values that you want to retrieve are things like the contact details of that friend, the languages spoken by the friend, and so on and so forth. All of those are regular subqueries that you are using to retrieve the final results from. This query is efficient to write. As you can see, it took a little longer to run because the shortest path execution is internally executed as a multi-step execution plan in SQL. That doesn't have its overhead, but in the end of the day, the efficiency with which you can express the query and the intent that you want to find answers to is really appealing. For most networks which do not have huge amount of skew in the way they're connected, like in a social network you can have a lot of skew in some cases, where a particular person may be connected to hundreds, if not thousands, if not millions of other people. For cases like that, shortest path identification can be sometimes more expensive than writing a series of chained match statements that we saw earlier. But in most cases, the shortest path query should execute as quickly as the naive approach that we saw earlier. So do give it a try, and you will be pleasantly surprised with the elegance of being able to express your queries using shortest path. The final demo that we have is to answer question 3 that we posed earlier in this presentation. As a recap again, that question is to start with a given person, go one step or two steps away and find all the friends that they're connected to. Then it gets more complicated in terms of expressing the kind of predicate that you want to express. You want to filter for all the messages that have been posted by these friends that you identified, but only those messages which have been in specified countries which we pass in as parameters to the query. And we have other filters, like those countries should not be the countries that these friends are normally resident within. This query may sound complex, but let's see how easy it is to to implement using SQL Graph. The way this query is implemented is you start by specifying the countries of interest. In this case, there are two countries of interest, Honduras and Estonia. You also specify the starting person for the search, which is this large number here. You also specify the time frame where these messages have been posted, and these two parameters are essentially being used to specify the time frame. The way this query is expressed is it involves using shortest path again to find paths of length 1 or 2 for people that this person knows. Once we find the friends or friends of friends that the initial person knows, we then have a CTE which wraps that query up, and then you write a filter which says, hey, we are only interested in messages which have been posted in a particular country and or in the other country. And we have filters in the where clause which say that these countries are the specific ones that we have been focusing on, and they are also not the ones that the friends are normally resident within. So the query can actually be compact and express the complex nature of the search conditions very efficiently. And when it runs, as you can see, you get the answer fairly quickly, and you have the list of friends that you have identified along with the amount of messages that they have posted in each of those countries. X count being in this case the amount of messages that they posted in country 1, and Y count being the amount of messages that they posted in country 2. So again, an example of how a complicated looking business requirement or a query can be very efficiently represented by using SQL Graph, match, and shortest path. Let's now take a look at some of the known good practices for SQL Graph. The first and foremost would be around indexing. I want to talk first about unique indexes on these graph columns, which are specifically the node ID and the edge ID for node and edge tables respectively. If you do not specify at the time of creation of the table a unique key on these columns, SQL will create one for you. It is highly recommended therefore to specify at the time of table creation unique indexes on the $node ID and on the $edge ID columns within the graph tables. This will later allow you to control not only the type of index, so for example you could say, hey, this is a clustered index, but also optionally disable the index if you wanted to when you're doing, let's say, bulk loading of large amounts of data. So highly recommended to create constraints and or indexes which specify the unique capability of the particular index, and also specify the node ID for node tables and edge ID for edge tables. Let's also talk about indexing when it comes to traversals. So the previous one I just talked about the uniqueness constraint and how that can be useful. In addition to the node and edge table unique indexes, it is highly recommended that we create indexes on the edge table to support graph traversals. This typically means that you will create an index on the from ID, to ID key combination. But in many cases, if you're expecting the traversal to go the other way, from the right to the left essentially, also consider creating a to ID, from ID. With shortest path queries, internally shortest path can actually pick either of the directions to traverse in. So consider creating both these indexes proactively rather than having to wait for a query tuning type opportunity to come up. As I said earlier as well, keep page compression if you can. In some cases, you can also consider using clustered column store index if needed, because clustered column store indexes can greatly cut down on the time it might take to do aggregations on the result set coming out of a match or a match with a shortest path. So usually we wouldn't do just clustered column store indexes. You would want to create the unique index and these from to from ID indexes that I mentioned, but you can always have a clustered column store and some of these indexes that we talked about. So keep that in mind, because graph traversals are point lookups typically, so you typically want to have the unique and the from to from, but clustered column stores can help in some cases as well. I want to talk briefly about a design situation that comes up sometimes, and we get these questions from customers saying, hey, why do you have edge constraints, and what's the story with allowing multiple edge constraints in a given table? Let's take a concrete example of what I'm referring to here. So imagine we have an edge table which is connecting person to let's say posts to person. So you have a has creator edge table which is connecting a post to a person. Okay, so you can actually use edge constraints, as I briefly showed you in the create table of our edge tables. We showed you how you can use edge constraints to specify that this edge table is only connecting posts to persons. Looks great, right? Now as the graph evolves, let's say you add a comment table which is a node table, and that comment table has more attributes or whatever, and now you want to have the same edge which is has creator also connect comments to person. So you would do that typically by saying, hey, let's add an edge constraint. This is the first reaction that you would have. You'd say, let's add an edge constraint to the has creator table which allows comments to be connected to persons. Unfortunately, this is the wrong thing to do, because when you add a constraint like this, when you already had a previous constraint saying post to person, let's say you added the second one which says comment to person, it's going to result in a situation where no row can be inserted into the edge table, because those rows will never satisfy both these criteria, post to person and comment to person. So keep in mind that an edge constraint is actually comprised of one or more edge constraint clauses. This is an edge constraint clause. You can have more than one of these if you wanted to, but when you have more than one edge constraint, it's going to add up. It's going to be an and in this kind of a situation where we have posts to person in one edge constraint and the next one saying comment to person, it's going to result in an impossible situation. So how do you fix this? The way to fix this is you're adding a new type of a constraint, right? You're saying you want to allow comments to person connections. So what you do is, as I mentioned in the previous slide, you can have multiple edge constraint clauses. Post to person is one edge constraint clause. Comment to person is another edge constraint clause. You can combine both of these into a single new edge constraint. So when you alter your table, you would say, hey, let's add a constraint which is a compound one which has multiple edge constraint clauses. This allows you to successfully insert new rows of the form, let's say, comment. But you cannot live in this situation forever. So the way you handle this is you add this constraint and then you immediately drop the previous constraint which allowed posts to person. When you do this, you end up with a table which effectively looks like this. You have a single edge constraint but with multiple edge constraint clauses. Post to person is one clause, comment to person is the second clause. So this is the way that we use multiple edge constraints to migrate a table from having just one possible set of connections to multiple sets of connections. I hope this clarifies a very common FAQ which comes from customers. When we have edge tables, you will sometimes come up with the question saying, hey, do we really need an edge table here, or can I live with a foreign key? Take the same edge table that we talked about earlier, which is the has creator table. You can have a constraint there saying, hey, this edge table connects post to person or comment to person. But when you really think of it, a post or a comment really just has one creator, which is one person, because that's a 1:1 kind of a mapping, right? You have one owner, one creator of that message. You generally will not have more than one creator. So while you can always use the graph edge table like has creator to connect the post and the comment to a person to indicate ownership or creator status, it might sometimes be more efficient to just model this situation as a traditional foreign key. It'll save you some space because you no longer have to have this many-to-many edge table to store what is essentially a 1:1 relationship, you can access the query using all your traditional T-SQL functionality. So just keep in mind, when you have many-to-many relationships, it's wonderful to model that using an edge table. In most other cases where you have 1:1 or 1:many, it might sometimes be advisable to just use a foreign key instead, a traditional foreign key. The other things that I wanted to share with you are around bulk insert. Bulk insert into node tables. One of the key things I already mentioned in the indexing best practices section was to try to disable those unique constraints or unique keys which were created on the graph table. Like for example, the unique key created on $node ID or the unique key created on $edge ID in the case of an edge table. But one of the key things here is to consider using node ID from parts if you can, to leverage natural keys if they were available, and if they were integers you can use node ID from parts and transform that natural key into the representation that is needed to insert into the $node_ID column. So as an example, in this case, in this demo, we're going to look at or in this sample, we have insert into the person table, where we are trying to pre-calculate or pre-formulate the $node_ID column by using the node ID from parts, which takes into account the object ID of the person table and the ID. This ID happens to be the integer that's present in the data set itself, so in the input data itself. This is a great optimization if you want to avoid subsequent joins to underlying data and the node table when you're later inserting into an edge table. So consider using natural keys if you can. That's the summary of this particular tip. And where sometimes it's not feasible, obviously you have no choice because it's a string or a GUID, which is the natural key. Then of course you have no choice. You let SQL pick the node ID column for you in that case. Similar to bulk insert into node tables, you have bulk insert into edge tables, and in this case there's a similar application of node ID from parts. So an edge table, let's say it has integer columns as the keys which indicate the from ID and the to ID of the data. Then you can use node ID from parts to formulate the $from ID and $to ID parts of the edge table as well. So just like the previous example, you have node ID from parts being used to formulate a from ID, which is actually going to be put into the $from ID within the edge table, and similarly for the $to ID. Again, as a reinforcement, why this is useful is if you did not do this, in this case, because it's feasible, you can do it. You would otherwise have to join the raw data that's coming in for the edge table with the graph node ID values from the node tables in order to get the $node ID values for the $from and $to ID columns. You get it, right? So it essentially avoids that complex and costly join. Again, it only works if your natural keys are integers. If they're strings or GUIDs, you just can't use this optimization. So very useful tip if you're going to be doing a lot of bulk inserting into graph tables. The last thing I want to mention is in terms of scaling. And while a given graph query generally can run very quickly if it's provided with the right set of indexes, for example, to run quickly, in many cases you want scalability which is beyond just one node. With the Azure SQL database, for example, you can use Azure SQL database hyperscale, which allows you to massively scale these read operations. And the tendency is on a real world graph, you will tend to have a lot of read enquiries or read queries on the graph. Writes, of course, will be a big part of the workload, but reads tend to be far more dominant in most cases. When you have lots of reads, you can scale them out by using things like Azure SQL Database Hyperscale, which allows up to 4 HA replicas and up to 30 named replicas. You can also use a similar pattern with SQL Server by doing always on availability groups and having scale out of your read queries there as well. Wrapping up, let's try to summarize some of the key points that we discussed. So the first thing, as you would have seen by now, is that many use cases in real life can benefit from a graph database and graph models, and that is where SQL Graph can really help you. It is not a question of graph database or relational database, as you saw. With SQL Graph, you can combine the best of two worlds, where you can have relational tables which are also graph tables, where you can take the trusted mature platform that SQL offers and overlay it with the functionality that SQL Graph provides. You do not need to learn new languages. You can use traditional T-SQL with these extensions that you saw, match, shortest path, node, edge tables, to query the graph. You also get for free all the goodness of SQL as a trusted platform with its scalability, reliability, all the other benefits that you have come to trust SQL with. You always have the flexibility of using traditional tools that you have come to expect and use with SQL. Say, for example, Power BI or management tools like Azure Data Studio, Management Studio, and so on. You have all the benefits of the flexible data types. Like you can store JSON and XML data. With that, you can have flexible schemas in the way without having to sacrifice the power and robustness that SQL Graph brings to the table. And where really needed, you can always go out of SQL using extensibility mechanisms or using the connector for things like Apache Spark and so on. So once again, thank you for watching, and for further reference we have a bunch of links in the slide deck. We hope that you will find those useful and furthering your knowledge when it comes to learning more about SQL Graph. Thank you again, and have a great rest of the day.